So we have Sarah today. She did an undergraduate degree at Leeds University with a master project on magnetohydrodynamics of shear flows in the sun. She then went to the Imperial College to do a PhD with Prof. Jonathan Mestel on linear stability problems of ferrofluid hydrodynamics. And now she's doing a postdoc at the Imperial College working on the same topic, and that's what she's going to present to us.
Hi, and thank you for inviting me to speak, and thank you in advance for listening. So I tried to do a screen recording of a video of ferrofluids for those who maybe aren't as familiar with them, and this is them responding to a magnetic field, and my whole PhD was basically looking at the linear stability of different configurations of ferrofluids subject to magnetic fields. Okay, so I'll just stop that if I know how. Oh, there we go. And sorry, I tried to put it into. Oh, how do I? View. Okay. So I was supervised by Professor Jonathan Mestel, and all my work has been on the linear stability of ferrofluids. So ferrofluids are colloidal fluids. They are comprised of magnetic solids, normally magnetite or other ferrites, suspended in a surfactant or carrier solution, normally kerosene or water. They're stable against agglomeration, which means they're thermally agitated so they can't join and then sediment. So you can imagine they're all suspended throughout the fluid. And they display a superparamagnetization. So when they're subject to a magnetic field, they might respond like this, and then when you remove the magnetic field, they then go back to their normal state. So advantages of them, as you can imagine, you can easily use the magnetic field to direct them where you want them to go. They can be held in place without any structural supports, and they're 10 to the 3 times more receptive than a normal paramagnetic liquid, which means you'd need a way weaker magnetic field, and which obviously reduces energy costs and just any physical restrictions. Also, so advantageous to a lot of applications is that they have a range of different carrier liquids, so you can almost cater the viscosity of the fluid to your application need by picking different liquids, and they heat up in response to an alternating current field. So applications involve dissipation of heat, so they're used in audio speakers, dampening of any resonances or any vibrations, magnetic jet printing, dynamic sealing, so they're used in floppy disks, for example, where you want the interior to rotate, but you want it to be free to rotate, but nothing to get in. So if you cover it with a ferrofluid, you're allowing for that to happen. They're also sometimes used or trying to be used in MRI contrast agents, and hypothermia therapy. So they're injected at the target sites of a tumor, and then you apply this alternating current, and they'll heat up and hopefully destroy the tumor without affecting the rest of the fluids. And magnetic drug targeting, and I've got just a little diagram for this. So the ferrofluid is combined with the cancer-curing drug, injected into the bloodstream, and you use the external magnetic field to the cancer site, and then the fluid is allowed to react with the cancer tumor and then hopefully destroy them. And in audio speakers, the voice is here, and the fluid surrounds it, and it carries heat away from the audio speaker, allowing high volumes to be met, and also it dampens any vibration, unwanted resonances. So the most famous linear instability, the most famous instability problem, and the first instability problem is Rosensweigs normal field instability problem. And you basically just have a ferrofluid and air or another magnetic medium, non-magnetic medium, and apply a normal field. And for a critical field strength, once it exceeds that, the system becomes unstable and reaches this new configuration of spikes. And there's been lots of literature on this. So I then wanted to look at the linear stability of ferrofluids in different configurations subject to non-uniform fields. So here we have a constant field, but I wanted to look at spatially varying fields. So I assume throughout the work that I'm going to show you that the ferrofluid is current-free. There's zero electric conductivity. It's an isothermal system, so there's no heating and no temperature changes, no physiochemical changes in the ferrofluid, no particle interactions. So these are like little magnetic particles, let's say, and they could interact by interparticle dipoles, van der Waals, but we assume there's no interactions. And that means that we're assuming there's quasi-stationary theory, and we're assuming the magnetization M is applied, is collinear with the field. So chi is magnetic susceptibility with the field, and by magnetic susceptibility of the ferrofluid. By assuming this, we're assuming that the relaxation time is instantaneous. Okay, so there's no relaxation times of the particles. Okay, so these are they're not non-dimensionalized. They've got the dimensions, but these are the governing equations. So this comes from Ampere's law, and it's the curl of H is 0. Gauss's law, this is B, if anyone's familiar with EHD or MHD, but when we're assuming that the field is collinear with the magnetization, it simplifies to this equation. Then we've got an incompressible fluid, and we have this forcing term, which is unique to ferrohydrodynamics. And this comes from the magnetic stress tensor. Now, if you notice, if we consider chi 0, so we don't have a magnetic fluid, we then get Maxwell's stress tensor in the absence of an electric field. And if we then take the divergence, we then get the forcing term. Now, so throughout my work, I've considered constant chi, and I've also considered a chi that depends on the field. So H is the modulus of the magnetic field, and it can, the chi, the magnetic susceptibility, can depend explicitly on the field, and it can also vary with position. And this affects the forcing term. So in its most general case, we have this more complicated forcing term. So we've got integral where the grad phi is held constant to h, and then the integral will be formed and you get your forcing term. But if chi doesn't depend explicitly on h, so if chi just varies with position, then it simplifies to a nicer form here. Okay, so because I'm allowing chi to depend on position and h, we then refer to Zalezo and Melcher. I probably pronounced his name wrong, sorry. And he assumes that d alpha I by dt is 0, where alpha I are physical properties of the ferrofluid. So that means that they're taking a parcel of ferrofluid, and if they were to move it, it retains any physical properties over a timescale of interest. For simplicity, we assume d chi by dt is 0. And if chi depends if chi doesn't depend on h, these are the same. But if chi depends on h, then we have a bit of a problem, because you'd imagine that if you had chi, a fluid property of chi which had an explicit dependence on h, and I move it to somewhere where h is different, you'd expect it to change its value. But so by assuming this, we have to also assume that it can have an initial dependence on h, but if we shift it, it then needs to retain its initial dependence. So we're assuming that that change in h is happening on a slower time process, and so that's to simplify the equations, really. So yes.
Viscosity is even a slower process.
What do you mean? The viscosity comes in the Reynolds, yes. In the Navier-Stokes equation. Exactly. So I'm not allowing for a change in viscosity.
I mean that I would presume that if you have a total derivative of your quantity of interest alpha I decided this term, you also have viscosity appearing, or maybe. You can explain it later.
I mean, I'm not actually sure.
Are you trying to interpret that like one of these equations?
Yes.
I guess simply trying to play with that kinematics still. And then, oh, is it zero? I suppose.
No, I think you're right. I think, yeah. Okay. No, please. So throughout my work, it's been a lot, because of the complicated nature of the forcing term with that integral, you could find that actually if you just take the curl, so if I take the curl of the forcing term, both the forcing terms appear as this when I take the curl, which proves a lot more easier to work with for my subsequent analysis. And from this, we can also see that for a stationary state, so if for an initial equilibrium where we have no velocity, that if chi varies with position and h varies with position but can be written in terms of chi, then we have a stationary state. Now this isn't chi does not have to depend explicitly on h, and h does not have to depend explicitly on chi. It solely means that we'll see later on that say chi varies in one dimension and h varies in that same dimension, so that I could write it as for the other, then I have a stationary state. Okay, so there's actually an analogy with electrohydrodynamics. I'm not sure if people are familiar with that, but if we have linear magnetization characteristics of the ferrofluid, and we have no current, then B, which is our induced magnetic field, these equations for the ferrofluid, you can see are analogous, I always have trouble saying that word, to a dielectric in EHD. So there's no free charge, and D becomes B, epsilon naught becomes mu naught, where that's the magnetic permeability of free space, and this is the electric permittivity, and E becomes H. Now, as pointed out by Rosensweigs, although they're analogous in their equations, experimentally you don't see the same effects as much. So, for example, the normal field instability I showed you, that even though it's the same in dielectrics, you wouldn't actually see that response experimentally, because ferrofluids react to such a smaller field strength, so you need a much larger electric field. But if we look at this experimental picture, this is a ferrofluid and this is a dielectric and this is the labyrinth instability. You can see they have a very similar pattern. So I guess the point of showing you this is that all the results of the ferrofluid could be applied to a dielectric. So this was the first problem that I looked at, and it's expanded on a lot of the ferrofluid literature, including some work that Mark had done. And this is a ferrofluid problem centered on a wire which brings a current which produces this azimuthal magnetic field that decreases radially. And we have another ferrofluid surrounding the inner ferrofluid. Now, we assume that chi, magnetic susceptibility, is constant in both of the fluids, and this means that the forcing term is zero in Navier-Stokes equations. And what we find is actually the forcing is confined to this interface between the two fluids, and this balances the capillary pressure and the two pressures of the system. So I considered a non-axisymmetric perturbation to the system, and so I produced an analytic solution to the Stokes equations, and then to a final constant you apply various boundary conditions, so your normal conditions for H and B, no slip of the wire. Oh, I should say, sorry, this is for arbitrary Reynolds number as well. No slip of the wire, conditions in the far field, and for example, kinematic conditions, stress, potential stress at the interface. And we get this expression for the growth rate. Now, arbitrary Reynolds number, G1 and G2, both depend on the growth rate as well as the Reynolds number and their functions. So we can't say much about it in its in this form. And this is to solve this equation, we have to solve it using a numeric root solver. But this B that appears here is the current, it measures the strength of the current through the wire and surface conditions of the capillary forcing.
Sorry, can I just ask,
Yes.
this linear problem
Yeah.
about some base.
Yes.
You've got flow.
No, so it's stationary, and it's stationary, and you have this H on like one over R.
Okay, so it's an instability and just a static.
Yeah, a fluid column. Yeah. So.
Sorry to interrupt.
Yeah, please.
Can you say on the next slide what it is that you're solving for? What are the unknowns in the? Is it equation on the slide there?
So M and K are the wave vectors. B is a known parameter. Chi1 and Chi2 are the susceptibilities of the fluid. And G1 and G2 are functions that involve these parameters, as well as S. And S is what we're solving for. So when I eventually solve it, I have to input the Reynolds number, all these variables as well. Sorry, I wasn't clear about that. So first of all, before using this numerical solver, I looked at the Inviscid limits and highly viscous limits, and in that case, you get an implicit expression for S. So you can actually show that the system is unstable if this is negative. Now, if we just go back to our initial problem, this G1 and G2 have now tended to other functions which no longer involve the growth rate of the perturbation. So we actually just get S equals this expression. So then, I don't know, we know from stability analysis, when that's greater than 0, we have an instability. So, less than 0. So S, G1 and G2 are positive, and we're finding that this is negative. If this is negative, you can see that if the inner fluid is more magnetic than the outer fluid, the only negative term is this -1. This is down to the capillary forcing. Okay? And then, the only unstable modes are axisymmetric modes. So when the inner fluid is more magnetic, the only unstable mode is the axisymmetric mode, and that agrees with all the literature, and that is basically what the literature says. But if you look at the outer fluid, so Chi2 being more magnetic than the inner fluid, then this term is actually negative. And if we increase the current in the wire, so increase that B, so increase the magnetic field, then this mode could be larger and larger and larger, and we could render axisymmetric mode, or we can render up non-axisymmetric modes unstable. Note that this is always positive because G2 is positive. So this is always stabilizing, but we find that by increasing B, this isn't big enough to affect it, and actually non-axisymmetric modes are unstable. So just to show some results briefly. So this is the Inviscid limit when the inner fluid is more magnetic than the outer fluid. And basically A to D, I'm just increasing the strength of the current through the wire, so I'm increasing the strength of the field. And you can see that the modes just become more stable, which is what we expect. And the red line, sorry, it's not very clear. The red line is the axisymmetric mode, and that's the only unstable mode when B is 0, so when there's no current in the wire. And similarly for the viscous, highly viscous, and this all agrees with the literature. But when we have the outer fluid more magnetic than the inner fluid, as I increase the field, so when I get to V equals 10, all the even the n=2 mode has unstable modes. And similarly for the highly viscous limit, but if we look at A=0.1, we actually see that for long waves, the n=1 mode, which is this blue dashed line, is actually the most unstable mode. And is probably a surprise because a lot of literature didn't consider non-axial symmetric modes because of they always assumed that the axial symmetric would be the most unstable. And this is seen in the Inviscid case, and it is seen when we increase this when A is 0.5, and A is the radius of the wire. Sorry if I should have probably said that before. So when the radius of the wire is bigger, this isn't happening. n=0 is still the most unstable. It's just when this radius of the wire is shrinking and we're looking at long waves that this is happening. And just to touch on the effect of the wire thickness, although it doesn't affect a mode, whether a mode is stable or unstable, it does affect the magnitude of the growth rate. So the smaller the radius of the wire, the larger the growth rate. Okay, so for arbitrary Reynolds number, like I said, I use a root solver, and I actually use medical, which I'm pretty sure no one uses, but I've said, do you? Great! I know. Everyone's always like, I'm using Google. So I use Maple and just use, I think it's just fsolve, and it just very simply solves the solution, solves the equation when you give it solutions. So this is, I thought I'd just show you some plots. So I found all the values that I tested for arbitrary Reynolds number, it behaves by that stability condition that was the case for this highly viscous. But so this is when the outer fluid is more magnetic than the inner fluid, and we've got a relatively low field strength here, and n=0 is this over here, and you can see that this is the real part of S's positives that are unstable, and n=1 is the stable mode, which for this field strength is stable. And we start at the viscous growth rate. Now this one is going off to -infinity, and that's because of the scaling for the Reynolds number. But they meet, and they then become complex conjugates of each other. And as we increase the Reynolds number, they then go to the plus and minus roots of the Inviscid case. And that agrees with our highly viscous and Inviscid limits. Now, as I said before, when the outer fluid is more magnetic than the inner fluid, if we increase the field strength, we render more modes stable, and we see that happens arbitrary Reynolds number as well. So I've now, by increasing the field strength, I've rendered that n=1 mode as unstable. So this is just to look at the effect of a small wire radius and long waves again. And you can see that for low Reynolds number, so as I go along, I'm increasing the Reynolds number. Sorry, the graphs are not very clear on here. I'm really sorry. So A to B to C to D to E to F, I'm slowly increasing the Reynolds number, and it's doing as we expect. Low Reynolds number, n=1 is off going to infinity. It's still the greatest mode here, but slightly as I increase the number, n=0 is becoming more unstable. And this is something that I want to explore more, and there was discussion that it might be to do with Stokes' paradox, but I would like to look at the long wave limit and explore it more. And then this is just to show when the inner fluid is more magnetic than the outer fluid. I showed that by increasing the current in the wire, I can stabilize that axisymmetric mode. So here we've got a lower strength of field, and the axisymmetric mode then becomes stable once I increase the field to b=0.5. But I didn't want, so now I've got the outer fluid more unstable. When the outer fluid is more magnetic than the inner fluid, increasing that current in the wire isn't stabilizing the system like it does when the inner fluid is more magnetic than the outer fluid. So you can show that by adding an axial field, so a field running parallel to the wire, you can stabilize all modes, and we get this stability condition here. And you can see that this new term, and Z is the strength of the field, and it multiplies K, the wave number, in the Z direction. So obviously, for long waves, this wouldn't work, so we'd have to omit long waves. But we can show that by increasing Z, making it sufficiently large, we can stabilize the problem irrespective of which fluid is more magnetic. So this got me thinking about, so when the outer fluid was more magnetic than the inner fluid, I had the magnetic forcing was creating an instability. Whereas before, when the inner fluid was more magnetic than the outer fluid, the magnetic forcing was stabilizing the system. So with that, if H is decreasing with R, so H looks like R, so it decreases radially in strength, one might think, if you think about a magnetic fluid, a stronger part of magnetic fluid would be attracted to maybe stronger parts of the magnet, let's say. So does this mean that when the susceptibility decreases radially, the system's happy because the stronger parts are where the field is strongest, and the other way, it's not happy and it's creating this instability. So what I wanted to look at was, what if I have this magnetic susceptibility varying with radius? So that was the next part, and so I consider an infinite column of ferrofluid centered along this same wire which produces the azimuthal magnetic field, and I look whether d chi naught by dr greater than 0 means they're unstable. So I've removed any forcing from the interface, the capillary forcing, and I'm looking solely at the magnetic forcing now. And performing linear stability analysis, you linearize the equations, and I get an eigenvalue equation, and I then use variational methods and a similar method to the Rayleigh-Ritz method, if people are familiar with this. And I can prove that if and only if d chi naught by dr is greater than 0 somewhere in the fluid, then we have this instability. So I'm not sure if you know that Rayleigh's criterion thing. It's a similar thing to that. And on top of that, I can also prove that a sufficiently strong axial field will stabilize the system. Again. Yeah, please.
So now the instability is no more at the interface because you don't have an interface. So where is the instability, or what is the form of your perturbation?
So you perform. So even before, I was perturbing every single variable. So I'm not just perturbing the interface. I perturb every variable. Sorry if I didn't make that clear. Yeah. So everything's perturbed everywhere. So having seen this result, which I guess fitted with my hypotheses, although the somewhere in the fluid is actually quite surprising considering it's a local condition that gives rise to this global instability, rather it's not just d chi naught by dr everywhere. So I then have to think about, if I have a non-uniform field and a non-uniform chi, does d chi naught by dh naught less than 0 mean instability? So if we look at this diagram here, and imagine H is decreasing upwards, and we have little fluid, and chi is strongest up here, and then decreases in strength, we might expect that this configuration has more energy than, say, this configuration than this configuration. So if I was to swap a parcel, there might be a release of energy which a perturbation is using to grow. And this is just a kind of theory, but this led us to find a new, another stationary state, and that is just have a planar configuration, a normal field acting varying upwards, and chi also varying with z. So they both only vary in one dimension, and for this to be a stationary state, we have to have this relationship. Now, this isn't a physical relationship. It isn't a chemical or physical process. So, for example, you can have a actual explicit dependence on chi and h, Langevin magnetization relation. It's not to do with that. It's just, if you imagine I take a chi of z and I apply this normal field, it adapts in such a way to satisfy the equations. Now, from this equation, we can see that declinal radiation will be negative. And so I might think it would be unstable to fit with the hypothesis. And performing the linear stability analysis and the perturbations, I proved that actually indeed S is greater than 0, so we have an unstable system. But we want to stabilize the system. So I looked at applying a constant field across the domain. And this doesn't work. There remains unstable modes. But if we apply a rapidly rotating field and it's sufficiently large, we can stabilize the system. Now, because we've got a time varying field, you need to think of Faraday's equation in Maxwell's. So I could be inducing an electric field. But because I'm assuming that there's 0 electric conductivity in the magnetic induction equation, this remains okay, and we assume that dB by dt is sufficient, is ignorable in Faraday's equation. But if I had a finite electric conductivity, that wouldn't be the same because my time scale is going to be very big. So that's the way of stabilizing the system. And then I started to think about a general. How much time do I have? Sorry. Oh, okay, way faster. I mean, okay, so then I started to think about a general high variation. And if I have just a volume of ferrofluid and I have a magnetic field, a non-uniform magnetic field, and a non-uniform magnetic susceptibility, if declinal by dH0 is less than 0 everywhere in D, would this be unstable? So this is another way of testing my hypotheses. So in other words, if that I0 and H0 aren't increasing at the same places or aren't aligned, these areas aren't aligned, am I getting stability? And using the same stability analysis, we can actually prove that if this is less than 0 somewhere in B, we have an instability. And that's provided that we have a stationary state. So at the beginning, if you remember, I said H0 is a function of chi, means that we could have a stationary state. So I assume that to be true. And if chi naught varies gradually with position, because the equations are very complicated, so by assuming that chi naught varies gradually with position, we can prove this condition as well as U is naught on the surface as well. So this is good because if we have a complicated equilibrium and we don't know whether it's going to be stable or unstable, and I don't know, it might be very computationally heavy to work this out, we could guess or gauge it from this stability condition. So to summarize, I first considered a piecewise constant phi, and when inner fluid was magnetically out fluid, the system was stable for non-axisymmetric modes, and a sufficiently strong B, so a sufficiently strong current through the wire, would stabilize the axisymmetric mode, so we'd retain this cylinder. But if the outer fluid is more magnetic than the inner fluid, and I increase that B through the wire, I'm then rendering more modes unstable. But an axial will stabilize the system provided long waves are emitted. I then look at a phi varying spatially and an H0 varying spatially, and I prove this condition for a cylindrical domain, and show that it's stabilized by an axial field. I proved that it holds for a chi naught H0 varying normal to the planar domain, and a general chi naught varies gradually with position. Now, application of these results. So, if we think back to our magnetic drug targeting, yes, a planar configuration might not quite be the way you'd model an artery or whatever, but this is almost more beneficial than a cylindrical domain, because even though cylindrical domain would be more like an artery, we have to have this wire running through it, which obviously is impossible in the body. But with this planar domain, we could imagine the walls of the blood vessel, and we can have this rapidly rotating field on the outside, direct it to where we want it, release this rapidly rotating field, and allow for dispersion the magnetic fluid. And similarly, there are a vast amount of different industrial applications as well, which will have different configurations. So we might have a cylindrical domain, we might have a planar domain. But a thing that has been asked me a lot is what is the kind of point of this high not varying satiety? And because often it's modelled as a constant susceptibility. If we think back to this MRI contrast agents, the way they work is they have all the different bits of tissue lined up, and they all have different susceptibility to a magnetic field. So rather than modelling them as lots of different little ones, we could imagine it as a continuum, and say then we can know what type of field we need for the MRI to work, or I don't know, something like so future work, I really want to look at the nonlinear work on the two-fluid system, especially when the outer fluid is more magnetic, and applying this axial field. I want to look at the results in long wave with a smaller radius of the wire. And I'd also like to find other equilibria to test this hypothesis, but it's really hard to find other equilibrium. So, but I would really like to do that, but it's because you have to satisfy all the equations. When I is non-uniform and H is non-uniform, it's quite tricky. And these are just a few of the references. And yeah. Sorry if I rushed that. It's too quick.
Plenty of time for questions. There are a few, Robert.
So I might have missed this earlier on, but your instability cylinder, you were doing things in terms of a Reynolds number.
Yeah.
So if it was a state without any flowing, how did you define the Reynolds number?
So I just non-dimensionalized. So I non-dimensionalized the pressure and the temperature, the time, with the viscosity of the fluid and the surface tension. And then you took it scaling accordingly.
Okay.
Does that make sense?
I think
So pressure was the surface tension over the viscosity.
So there's some velocity scale that comes out.
There's a velocity scale that depends on the pressure and the I keep saying temperature, time.
Okay.
Okay.
So can you just go back to the slide where you showed it was the cylinder with the two kinds, I think. When you were showing S. Just keep going back and I'll tell you in a minute. That was very good.
This one?
That was just the bit where the two modes, the two eigenvalues merge and become complex at about 70. I'm just curious, how does that value change with the parameters to know? If you play with A, what parameters have you got left?
So you can change A, you can change K, you can change chi1, and you can change chi2.
Okay, right, so there's lots of freedom.
There's lots of freedom.
Did you just do one case?
No, I tried lots of different ones, but I actually can't remember at the top of my head because I did that this was my first year work. So, but I'm happy to try again on the Maple. I still have it, so I can just plug them in basically. But it definitely did move, but I can't remember for what values it moved. But it's never the same Reynolds number. It did vary. I just can't remember.
And you always see a merging. I was wondering if it was complex straight off.
No, so this characteristic happens no matter what.
So zero Reynolds number, it's always real.
Yeah, and that's because so for the viscous fluid, you get an expression for the highly viscous, you get an expression for S, but for the inviscid, you get an expression for S squared. So we wouldn't expect, and we wouldn't expect there to be a solely imaginary one at low Reynolds number. We'd want that to always be real, because that's what we found in the highly viscous limit.
Yeah, it's complex in general.
Yeah. So this will slowly go to zero, and these slowly tend to the positive and negative values of the Inviscid growth rate. Yeah, please.
Can you define a Hamiltonian of the system or energy of the system?
So Mark also asked me to do this, and basically, so the energy, the change in energy, if you have you remember we were talking about lunch, how I was saying in the book, the main, like Rosensweigs book, so the main book on ferrohydrodynamics, so it was quite complicated in their terms. So, okay, I'm just gonna, basically, the way I interpret it is, yes, so you take a volume of ferrofluid, you take a volume of liquid or a volume of fluid, and you already have an H set up, so you already have a field set up, and the change in energy when you introduce this ferrofluid becomes, I guess I can't write anything, becomes, it's not complicated, so it becomes minus, it's a minus integral of the magnetization,
I don't know very well, but okay.
Well, so it's a minus integral of n, which is the magnetization, dotted with H naught over DH. And H naught is the initial field that you have before, but the magnetization. So if I use my collinear approach, which is what they do in the book as well, so M is chi H. This H is the change, but it's dotted with the initial. And I don't know, I found it a bit confusing as to what to do with my my problem. But if I assume that H stays the same, because you can have this H naught is 1 over R before adding the ferrofluid and when you add it, so it satisfies the equation no matter what. And I assume that I have this, so H, modulus of H is 1 over R. If it's collinear, they can just be written as moduluses. So I have chi over R dr, so because it's a cylindrical system, from A, which is the radius of y to the infinity. So this would be the change in energy. And what this tells us is that this will be minimized when all of the chi is largest, where R is smallest, which is what we thought to begin with. But interestingly, it's not saying anything about this gradual decrease that we were finding. So actually we find it doesn't have to be clumped there, it could just be gradually decreasing. And this doesn't necessarily tell us that d chi by dr greater than 0 somewhere would give an instability. But yeah, this is what you can for the energy change.
I was indeed thinking about, well, the argument that you sketched.
Yeah. So that's,
see this through an energy argument.
Yeah, that's what was. I felt like intuitively it made sense that they would be, that they'd want to be where the field was largest, and it is what it tells you that, but you can't make it doesn't go as far as the linear stability analysis told us. But thank you for that question.
You don't explain to me, but what kind of functions are G1 and G2?
So lots of modified Bessel functions. So the yeah. So you're welcome to look at the appendix of my thesis, where it's pages long, because the analytical solution of the Navier-Stokes is a modified Bessel function,
Which has like limits. It has like.
Yes, so you have to. So for example, you can't have Bessel I for the outer fluid because it's going off to infinity, and but because I have the wire, you have a condition at the wire which has, so that there's also a magnetic field in the wire, and that one can't have Bessel I, but that has to be matched with a condition at the wire. So the first fluid can have Bessel I and Bessel K, but there's a boundary condition at the wire. And so these functions involve.
The plots are going off to infinity because it's bound.
Yeah, so in the wire you can't have vessel K because at r equals 0, vessel K goes up to infinity. But fluid 1, you can have both the vessels because you have a boundary condition. So all the G1s and the G2s. So here, the argument of the modified vessel functions have the Reynolds number and S and K in, and R. And
so it's an RCD to,
pardon?
So it's an RCD, it's like a transcendental equation.
Yeah, exactly, it is. So, but when you then take the inviscid and highly viscous limits, the modified vessel functions no longer have a dependence on S.
Cool.
Okay. I think we asked enough questions so far, and we can have some more at the coffee break in S120. So let's thank again Sarah.
And thank you all for listening as well, and your really good questions.